66 million years ago, something struck the Earth. It was about 6 miles wide. It hit what is now the Yucatán Peninsula, and within a short span of time, roughly three-quarters of all species disappeared. We know this part of the story. A thin layer of iridium circles the globe. A buried crater more than 100 miles wide lies beneath Mexico. Shocked minerals and glass beads still mark the boundary in stone, but the impact is only the end of the story. Before it became a crater, it was a traveler. It carried minerals formed in the earliest days of the solar system. It drifted somewhere beyond the inner planets, shaped by collisions, radiation, and gravity long before Earth had forests or dinosaurs. For millions, perhaps billions of years, it orbited the sun unnoticed. Then something changed its path. Gravitational nudges, orbital shifts, a slow inward migration through space. And at one precise moment in deep time, its trajectory intersected with Earth. That crossing altered the future of life. But where did it begin? Was it born in the outer asteroid belt? Was it flung inward by Jupiter's gravity? Did it originate far beyond where Earth now orbits? Tonight, we trace that ancient path backward, beyond the fire, beyond the crater, into the distant birthplace of the stone that altered life on Earth. But before we begin, I'd love to know, where in the world are you listening from tonight, and what time is it there? I read all your comments, and they are one of my favorite parts of this sleepy little community. If you're enjoying these late-night explorations, a like and a subscribe would mean a lot. And for those already subscribed, thank you for being part of this calm little corner of science. So now take a deep breath, let your shoulders loosen, and together let us follow the stone back to the darkness where its journey began. The morning sky above the shallow sea that once covered what is now the Yucatán Peninsula held no warning. Beneath warm coastal waters, thick layers of limestone and evaporite rock rested quietly, built from ancient marine life and long vanished tides. The air moved as it always had, indifferent to the object descending toward it at roughly 12 miles per second, a speed so immense that distance vanished almost instantly. When it struck, contact lasted less than a heartbeat. The asteroid did not simply collide with the surface, it delivered energy faster than the surrounding rock could respond. Compression raced outward in a violent pulse, forcing stone to behave like liquid under sudden crushing pressure. Temperatures climbed beyond those found at the surface of the sun. In that immediate flash, bedrock vaporized, seawater exploded into steam, and a transient cavity opened in the crust, wider than many mountain ranges and deeper than the tallest peaks are high. A brilliant plume surged upward through the atmosphere, carrying molten droplets and pulverized rock beyond the edge of space. Beneath that rising column, the ground rebounded, then collapsed inward, forming the immense crater that would later be buried under layers of sediment and jungle. The shock wave expanded in every direction, a ring of compressed air and superheated debris moving faster than any storm. Seismic waves radiated through the planet's crust and mantle, stronger than any earthquake measured in human history. Fault lines shifted continents away, and distant shores felt the trembling as if struck by a colossal hammer. The oceans responded next. Displacement of water around the impact site formed waves that climbed hundreds of feet high, racing outward across ancient seas. When they reached coastlines far from the point of impact, they scoured landscapes, stripping life from the land before withdrawing again. Above the surface, fragments of ejecta arced through ballistic paths, some falling back near the crater, others traveling across hemispheres. As these incandescent fragments re-entered the atmosphere, friction ignited them. The sky itself seemed to kindle with streaks of fire. Heat from countless re-entering particles spread across continents, drying vegetation and igniting widespread wildfires. Forests far removed from the initial blast found themselves under a rain of glowing debris. Within hours, fine dust and vaporized minerals began to accumulate high in the stratosphere. Sulfur released from the vaporized rock mixed with atmospheric gases, forming aerosols that reflected sunlight. The luminous plume that had risen so violently now gave way to a growing veil encircling the globe. Daylight dimmed gradually, filtered through a thickening haze that muted color and warmth. What began as a single point of contact became a planetary transformation. The immediate devastation near the crater was total, yet the wider consequence unfolded more slowly. As debris settled and fires burned, sunlight struggled to reach the surface. Photosynthesis faltered. Food webs that depended on steady light and stable climates entered a period of abrupt stress. The moment of impact was brief, measured in seconds and minutes. Its physical effects were recorded in shock waves, tsunamis, and layers of debris that would later harden into stone. Above all, it marked the beginning of a prolonged twilight, the first stage of a global darkness that would reshape ecosystems across land and sea. Long after the fires faded and the dust settled into quiet layers, the planet began recording what had happened in the most patient way it knows, by pressing memory into stone. Across continents, separated by oceans, in cliffs overlooking seas, and in road cuts carved through hills, a thin boundary emerged between one chapter of life and the next. It was not dramatic to the eye at first glance, only a narrow band, no thicker than a finger in many places, resting between older limestone and younger sediments. In the late 20th century, geologists studying these boundary layers noticed something unusual within that thin seam. Chemical analyses revealed elevated concentrations of iridium, an element that is rare in Earth's crust, yet more common in certain types of meteorites. On Earth, most iridium sank toward the core during the planet's early differentiation, carried downward by molten iron billions of years ago. Surface rocks therefore contain only traces. Asteroidal material, formed from more primitive solar system debris, retains higher proportions. The anomaly appeared not at one location, but in samples collected from Italy, Denmark, New Zealand, North America, and beyond, each revealing the same subtle enrichment. This uniformity suggested a global source, rather than a local volcanic eruption or isolated deposit. Fine particles within the boundary layer were examined under microscopes, revealing tiny glassy spherules, droplets that had once been molten and cooled rapidly while suspended in the air. Their shapes were smooth and rounded, evidence of liquid rock sprayed outward, then frozen during flight. Some contained mineral compositions matching crustal material heated to extraordinary temperatures. Another clue lay hidden within grains of quartz. Under immense pressure, quartz crystals develop microscopic planar features known as shock lamellae. These structures cannot be formed by ordinary tectonic processes or standard volcanic activity. They require abrupt compression at pressures far beyond those of typical earthquakes. When geologists identified shocked quartz within the same thin boundary layer, in regions thousands of miles apart, the pieces began to align into a single coherent event. The debris was not distributed randomly. Mapping of spherules, shocked minerals, and iridium concentrations showed patterns that thinned with distance from a point in the region of present-day Mexico. Core samples extracted from ocean floors contained the same signature, preserved within marine sediments laid down quietly after the catastrophe. Even microscopic fossils embedded within these layers bore witness to sudden environmental change, marking an abrupt biological turnover coinciding precisely with the chemical anomaly. To confirm that these signals represented one moment rather than multiple smaller impacts, scientists compared isotopic ratios within the iridium and other platinum group elements. The fingerprints were consistent across continents, pointing toward a single extraterrestrial source rather than scattered meteor showers. Radiometric dating of minerals above and below the boundary narrowed the timing to a geological instant around 66 million years ago. What emerged was not merely a hypothesis, but a convergence of independent lines of evidence. Chemistry, mineral physics, stratigraphy, and paleontology all trace their observations back to the same narrow horizon in rock. The Earth had archived the arrival of a cosmic object within that thin band, a global signature pressed into stone. The boundary layer, modest in appearance, yet vast in implication, became a marker recognized around the world, a quiet line separating the age of dinosaurs from the world that followed. Beneath layers of younger sediment and dense tropical vegetation, the scar itself lay hidden, its outline softened by time and concealed from ordinary view. There was no towering rim rising above the horizon, no open basin visible from the ground. Instead, the structure rested quietly below the surface of what is now the northern Yucatán Peninsula, masked by limestone platforms and coastal plains that revealed little of the violence once centered there. The first hints emerged not from the search for extinction, but from the search for oil. In the 1970s, drilling operations conducted by Mexico's National Petroleum Company brought up core samples that puzzled geologists. Instead of the flat, undisturbed sedimentary layers expected in that region, they encountered fractured rock, breccias, and unusual melt materials deep below the surface. These rocks appeared disturbed in ways that suggested extreme forces, yet at the time they were cataloged primarily for their economic context. Around the same period, geophysicists studying gravity measurements over the peninsula began to notice a subtle circular pattern. Variations in the strength of Earth's gravitational field can reveal differences in density beneath the ground. Instruments carried by aircraft traced a broad ring-shaped anomaly, a faint but consistent signal implying a massive, buried structure more than 100 miles wide. Magnetic surveys added further detail, outlining concentric features that hinted at a complex internal architecture. When researchers overlaid these geophysical maps with seismic reflection data gathered for hydrocarbon exploration, a remarkable picture began to form. Waves sent into the ground and reflected back to instruments revealed layered patterns bent downward in a circular depression, along with a central uplift where deeper rocks had rebounded upward. This configuration matched the known structure of large impact craters observed elsewhere in the solar system. On the Moon and on Mars, similar central peaks rise within expansive basins formed by high-energy collisions. Samples retrieved from drill cores were re-examined in light of the global boundary layer, already recognized in distant outcrops. Within the Yucatan cores, scientists identified impact melt rocks and shocked minerals consistent with those found at the extinction boundary. Radiometric dating of these materials yielded an age close to 66 million years, aligning precisely with the thin, iridium-rich layer observed around the world. The crater's diameter, extending over 100 miles, placed it among the largest known impact structures on Earth. Its scale accounted for the widespread distribution of ejecta and the magnitude of environmental disruption inferred from geological records. Modeling of the impact energy based on crater dimensions supported the idea that a body several miles across would have been required to produce such a basin. Gradually, independent lines of evidence converged. Geochemistry linked the boundary layer to extraterrestrial material. Mineral physics pointed to extreme pressures. Geophysical mapping outlined a circular depression of appropriate size and age. What had once appeared as fragmented clues, separated by disciplines and geography, assembled into a coherent whole. The structure beneath Mexico came to be known as the Chicxulub crater, named after a nearby town. Though hidden from direct sight, its presence is unmistakable in subsurface maps and drilled cores. It rests quietly beneath coastal waters and limestone shelves, a vast ring etched into the crust. From orbit, it cannot be seen with the naked eye, yet within scientific charts, its shape is clear and unmistakable. The buried basin stands as the physical imprint of the event recorded in stone layers worldwide, anchoring abstract chemical signatures to a specific place on Earth's surface. In laboratories far from the peninsula where the structure lies buried, fragments no larger than grains of sand became the focus of quiet attention. These particles, gathered from boundary clay and drill cores, were placed beneath microscopes and inside mass spectrometers, their elemental patterns coaxed into view through beams of light and carefully tuned detectors. Within their structures, subtle proportions of metals and minerals held traces of a body formed long before Earth's continents assumed their present shapes. Chemical analyses revealed that the impacting object was not composed of simple iron alone, nor of dense metallic alloys common in some meteorites. Instead, the debris carried signatures consistent with a carbon-rich chondritic material. Tiny inclusions within melt fragments contained elevated levels of carbon compounds, along with ratios of chromium, osmium, and other trace elements that align closely with a class of primitive asteroids known as carbonaceous chondrites. These meteorites are among the most ancient materials preserved in our collections, preserving chemistry that dates back to the early solar nebula. Embedded within certain boundary samples were microscopic minerals altered by heat, yet still retaining evidence of hydrated phases. Clay minerals and altered silicates pointed to the presence of water-bearing components within the original asteroid. In space, such hydration does not imply oceans or flowing streams, but rather chemical reactions between rock and ice in the parent body long ago. The presence of these minerals suggests that the object formed in a region of the solar system where temperatures were low enough for water ice to exist alongside rocky material. Isotopic studies provided further refinement. Ratios of oxygen isotopes within surviving mineral fragments were compared to known meteorite groups cataloged in museums and research institutions. The values clustered near those typical of certain carbonaceous bodies originating in the outer portion of the main asteroid belt. Platinum group elements found within the boundary layer displayed patterns consistent with this same classification, reinforcing the conclusion drawn from multiple independent chemical pathways. These compositional clues matter because different regions of the solar system produce distinct chemical fingerprints during formation. Temperature gradients in the protoplanetary disk influenced which elements condensed into solids and where ice could remain stable. Bodies that formed closer to the Sun tended to be more depleted in volatile compounds, while those farther out preserved greater fractions of water and carbon-rich material. By examining elemental abundances and isotopic signatures, researchers can narrow the likely zone in which the impacting body accreted billions of years ago. Comparison with known meteorites has been essential. Samples of carbonaceous chondrites recovered after falling through modern skies provide tangible benchmarks. Their textures, mineral assemblages, and isotopic ratios serve as references against which boundary debris can be measured. While no fragment from the crater can be matched to a specific parent asteroid with complete certainty, the chemical resemblance to these primitive types remains strong. Over time, laboratory techniques have grown more precise, allowing detection of minute variations in trace elements and isotopes. Each refinement has strengthened the impression that the Chicxulub impactor belonged to a carbon-rich lineage rather than a metallic or purely rocky class. Its chemistry links it to a population of ancient bodies that have changed little since the early solar system, carrying within them preserved records of that formative era. Through the language of elements and isotopes, the stone that altered Earth reveals the region of space in which its story likely began. Long before continents settled into familiar outlines or oceans gathered in their basins, the material that would one day become Earth drifted within a vast, rotating cloud. About 4.6 billion years ago, a region of a cold molecular nebula began to collapse under its own gravity. As it contracted, conservation of angular momentum caused it to spin faster, flattening into a wide disk of gas and dust surrounding a brightening center. At the heart of this disk, pressure and temperature rose until nuclear fusion ignited and the young sun began to shine. Around this early sun, the protoplanetary disk shimmered with fine grains of silicates, metals, and ices. These particles, smaller than grains of sand, orbited in nearly the same plane, moving in gentle, intersecting paths. Collisions were frequent, yet at first they were soft enough for grains to stick together through electrostatic forces. Clusters formed, fragile and porous, drifting within the gas like slow-moving snowflakes in a luminous storm. Over time, these aggregates grew heavier. Gravity began to assist cohesion, drawing nearby fragments inward. Pebbles became rocks. Rocks became kilometer-scale bodies known as planetesimals. Their growth was not uniform. Regions closer to the sun, where temperatures remained high, favored the condensation of refractory materials, such as metals and silicates. Farther outward, beyond what astronomers call the frost line, water ice and volatile compounds could solidify, adding mass rapidly to forming bodies. Within a few million years, certain planetesimals dominated their neighborhoods. Through runaway accretion, they swept up surrounding material, increasing in mass and gravitational reach. Protoplanets emerged, colliding and merging in a prolonged phase of chaotic assembly. Impacts were common, reshaping surfaces and redistributing material. Some collisions were gentle unions, others violent enough to melt entire bodies. The architecture of the inner solar system gradually took form through this persistent exchange of matter. Mercury, Venus, Earth, and Mars solidified from this process, their compositions reflecting the temperature gradients of their birthplaces. Giant planets accumulated farther out, where abundant ices enabled rapid growth of massive cores capable of capturing thick envelopes of gas. As these large bodies matured, their gravitational influence intensified, stirring the remaining disk and clearing pathways along their orbits. Yet, not all material found a permanent home within a planet. In certain regions, especially between the orbits of Mars and the growing giant planet that would become Jupiter, gravitational perturbations disrupted stable accumulation. Collisions continued, but repeated stirring prevented the fragments from coalescing into a single world. What remained was a population of rocky and carbon-rich bodies, remnants of the early building process that never completed their transformation into a planet. These leftover objects preserved conditions from the solar system's infancy. Shielded from extensive melting and differentiation, many retained primitive mineral assemblages and isotopic signatures dating back to that original cloud. Within their interiors, time slowed. While planets evolved through tectonics, volcanism, and atmospheric change, these smaller bodies remained relatively unchanged, orbiting quietly in the belt that marked an interrupted chapter of planetary growth. The early solar system was therefore not a perfectly efficient machine, but a dynamic and selective environment. It constructed worlds and left behind fragments shaped by gravity and temperature, by distance from the sun and the disruptive pull of neighboring giants. Among those fragments were stones carrying ancient chemistry, survivors from an era when the sun was new and the planets were still assembling from drifting dust. Between the orbit of Mars and the wide path traced by Jupiter lies a region that appears, at first glance, almost empty. From a distance, it is only a stretch of space, a quiet span measured in astronomical units rather than miles. Yet within that interval circle millions of rocky bodies, each following its own path around the sun, bound together not by touch but by shared origin. This region, known as the asteroid belt, occupies a zone where early planetary building was interrupted. During the youth of the solar system, solid material accumulated there, just as it did elsewhere. Planetesimals formed, merging through countless gentle and violent collisions. Some grew to hundreds of miles across, large enough for gravity to pull them into roughly spherical shapes. Others remained irregular fragments, shards of rock and metal left from earlier encounters. The environment between Mars and Jupiter might once have produced a full-sized planet. There was sufficient material in the disk for accretion to begin, and the same physical processes that shaped the terrestrial worlds were at work, yet a powerful influence loomed nearby. Jupiter, gathering mass rapidly from the outer disk, became a dominant presence long before the smaller bodies in the belt could assemble into a coherent world. As Jupiter's gravity strengthened, it stirred the orbits of nearby planetesimals. Gravitational resonances developed, zones where the timing of an object's orbit lined up in simple ratios with Jupiter's own period. In these locations, small periodic tugs accumulated over time. Rather than settling into stable circular paths, bodies within these resonant zones found their orbits stretched into elongated shapes. Speeds increased, trajectories crossed, and collisions became more energetic. These repeated disturbances prevented long-term calm accumulation. Instead of merging gently into a single large body, many objects shattered upon impact. Fragments from those collisions created families of asteroids sharing similar orbital characteristics and compositions. Over hundreds of millions of years, this cycle of disruption and reassembly sculpted the belt into a population of diverse remnants rather than a unified planet. The mass remaining in the belt today is only a fraction of what would be required to form an Earth-sized world. Much of the original material was scattered inward toward the Sun or outward beyond Jupiter, redistributed during the early chaotic phases of planetary migration. What persists is a diminished yet ancient assembly of bodies that retain evidence of those formative interactions. Within this broad band, composition varies with distance from the Sun. Closer to Mars' orbit, asteroids tend to be more rocky and metal-rich, reflecting the higher temperatures present during their formation. Farther outward, toward Jupiter's realm, carbon-rich bodies become more common, preserving volatiles and hydrated minerals that condensed in cooler regions. This gradient mirrors the temperature structure of the early disk, fossilized within orbiting fragments. Collisions continue even now, though at lower frequencies than in the past. When two asteroids meet, they may merge into a rubble pile held together loosely by gravity, or they may break apart, creating fresh debris that gradually disperses along similar orbits. Solar radiation and subtle gravitational influences slowly modify their trajectories over immense spans of time. The asteroid belt therefore represents an unfinished chapter of planetary construction. It is neither void nor fully formed, but a dynamic archive suspended between Mars and Jupiter, shaped by gravity's competing influences and preserved as a record of the early solar system's restless beginnings. Across the asteroid belt, patterns emerge when orbits are plotted with care. What first appears as a scattered swarm begins to reveal subtle clusters, groups of bodies sharing similar paths, inclinations, and distances from the Sun. These clusters are not random gatherings, but the lingering outlines of ancient collisions, moments when a larger parent body shattered and sent fragments outward along related trajectories. When an asteroid experiences a catastrophic impact, the energy released can fracture it into hundreds or even thousands of pieces. Though each fragment departs with its own velocity, their initial motions remain influenced by the orbit of the original body. Over immense spans of time, gravitational perturbations and thermal forces alter their paths, yet a common ancestry can still be detected in the geometry of their motion. Astronomers identify these groupings by comparing orbital elements such as semi-major axis, eccentricity, and inclination, searching for families that occupy a shared region of orbital space. The concept of asteroid families transforms the belt from a chaotic field into a record of generational history. Each family marks the site of a former worldlet, a body once intact and now dispersed. Some families are young in astronomical terms, their fragments tightly clustered and compositionally uniform. Others are ancient, spread thin by time, their members more widely dispersed yet still statistically linked. Beyond orbital similarity, composition offers a second layer of confirmation. Light reflected from asteroid surfaces carries information about mineral content. Using spectroscopy, scientists measure the intensity of reflected wavelengths and compare them to laboratory spectra of known minerals and meteorites. Certain asteroids display dark, carbon-rich spectra with subtle absorption features indicating hydrated minerals. Others reflect brighter signatures consistent with silicate-rich or metallic surfaces. Within a family, spectral patterns often align, reinforcing the conclusion that these bodies share a common origin. By combining dynamical grouping with spectral analysis, researchers reconstruct partial family trees. They can infer the approximate size of the parent body, estimate the energy required to disrupt it, and sometimes determine when the collision occurred. Cosmic ray exposure ages measured in meteorites recovered on Earth provide additional hints. When a fragment breaks free from a larger body, its surface is newly exposed to space radiation. The accumulation of specific isotopes allows scientists to estimate how long that fragment has traveled independently. These methods have implications beyond classification. If the debris found within the extinction boundary carries a chemical signature consistent with carbon-rich chondritic material, and if certain asteroid families in the outer portion of the belt exhibit matching spectral properties, a potential connection emerges. Although it is rarely possible to point to a single surviving asteroid as the exact source, scientists can narrow the field to particular regions and lineages. Meteorites that fall to Earth today act as physical representatives of these families. Laboratory comparison between their isotopic ratios and the traces embedded in ancient boundary layers strengthens or weakens proposed links. When platinum group elements, chromium isotopes, and oxygen signatures align within expected ranges, the narrative tightens. The stone that once crossed Earth's path becomes part of a broader familial context, a fragment likely born from a larger body disrupted long ago. Through the patient study of orbits and light, of isotopes and mineral grains, the asteroid belt reveals itself as an archive of broken ancestors. Within its scattered populations, relationships endure, allowing scientists to trace fragments backward through time and space. toward parent bodies that no longer exist in one piece yet still speak through their dispersed remnants. Far beyond the orbit of Mars, a colossal presence circles the Sun with slow authority. Jupiter, more massive than all the other planets combined, bends space around it in subtle but persistent ways. Its gravity extends far beyond its visible cloud tops, shaping the architecture of the solar system through influence rather than contact. Every small body that ventures near its domain must account for that pull. Jupiter's mass grants it a dual role. In many cases, it serves as a distant guardian. Objects drifting inward from the colder outer regions often encounter its gravitational well first. Some are captured temporarily, looping in elongated paths before being flung outward again. Others collide with the planet itself, swallowed by its thick atmosphere and lost from the inner solar system. Through these interactions, Jupiter reduces the number of long-period comets that might otherwise cross Earth's orbit. Its presence intercepts a fraction of potential threats long before they approach the Sun more closely. Yet the same gravity that removes certain objects can redirect others. When a small body passes near Jupiter without being captured or ejected, its trajectory can be altered subtly or dramatically. A change in velocity of even a few meters per second, insignificant on human scales, can shift an orbit over millions of years. A previously stable path may become elongated, dipping inward toward the terrestrial region. In this way, Jupiter can act not only as a shield, but also as a sculptor of orbital pathways, sending fragments from the asteroid belt onto new courses. Within the belt, gravitational resonances mark locations where orbital periods form simple ratios with Jupiter's year. In these zones, repeated tugs accumulate gradually. A body orbiting the Sun twice for every orbit of Jupiter, for example, receives a rhythmic gravitational nudge at the same point in its path each cycle. Over extended timescales, these periodic influences can increase orbital eccentricity, stretching a once nearly circular orbit into a more elongated shape. As eccentricity grows, the asteroid's path may begin to cross the orbit of Mars and eventually extend toward Earth's region. This transformation does not occur abruptly. It unfolds through small adjustments, compounded over immense durations. The process resembles a slow drift rather than a sudden leap. Each close approach to Jupiter modifies the trajectory slightly, and the cumulative effect can redirect material from the belt into Earth-crossing orbits. Simulations of the solar system's dynamics illustrate how sensitive these pathways can be. Minor differences in initial position or velocity can lead to diverging outcomes over tens of millions of years. Some fragments are drawn inward, others are expelled entirely from the solar system. Jupiter's gravitational field creates both gateways and barriers, shaping the distribution of small bodies across time. The Chicxulub impactor, if it originated within the asteroid belt as its chemistry suggests, would likely have traversed such a gravitational landscape. It may have lingered in a relatively stable region for ages before drifting into a resonance zone. There, persistent nudges could have altered its orbit enough to send it gradually inward. Jupiter did not aim it with intention, yet through the impartial mathematics of gravity, it helped determine which fragments remained distant and which found new trajectories. In this vast celestial arrangement, Jupiter's presence ensures that the solar system is not static, but continually evolving. Its immense mass anchors the outer architecture while quietly modulating the motion of smaller bodies. Through shielding and scattering alike, it shapes the pathways along which ancient stones travel, sometimes steering them away from Earth, and at other times guiding them toward the inner worlds. An orbit can appear calm when viewed in a single moment, a smooth ellipse drawn neatly around the sun, repeating with quiet precision year after year. Yet beneath that apparent regularity lies a delicate balance of gravitational influences. Some pathways through the solar system remain stable for billions of years, preserving objects in predictable rhythms. Others are only temporarily settled, their geometry gradually shifting under the persistent pull of neighboring worlds. Within the asteroid belt, this contrast between stability and instability is etched into its very structure. When astronomers chart the distribution of asteroids by distance from the Sun, they do not find a uniform spread. Instead, distinct gaps interrupt the population. These regions, known as Kirkwood gaps, correspond to orbital resonances with Jupiter. An asteroid orbiting at one of these resonant distances completes a specific fraction or multiple of Jupiter's orbital period, creating a repeating gravitational alignment. In such resonant zones, even small gravitational tugs accumulate with time. Each encounter may be slight, altering speed or direction by only a fraction, but repetition is relentless. Over tens of thousands, then millions of orbits, these periodic nudges stretch the shape of an asteroid's path. Eccentricity increases. The once circular orbit grows elongated, crossing the paths of Mars or extending inward toward Earth. What had been a relatively safe corridor becomes a dynamic bridge into the inner solar system. The transition from stability to instability often unfolds slowly, almost imperceptibly. Thermal forces such as the Yarkovsky effect, in which absorbed sunlight is remitted as heat and produces a minute thrust, can shift an asteroid's semi-major axis over immense spans of time. A gradual drift of only a few kilometers per million years may eventually guide an object into a resonant zone. Once there, gravitational interactions amplify the change. This interplay creates what researchers sometimes call orbital highways. These are not physical roads, but dynamical pathways that channel material from the belt toward Earth-crossing trajectories. An asteroid entering such a corridor does not accelerate toward Earth immediately. Instead, its orbit evolves through a sequence of gravitational exchanges, each adjustment subtly reshaping its route. The timescales involved dwarf human history. Tens of millions of years may pass as a fragment migrates from a stable cluster into a resonance gap. Computer simulations reveal how sensitive these journeys are to initial conditions. A minute variation in starting position can result in a vastly different outcome over geological durations. Some objects are scattered outward, others spiral inward, and many settle into new, long-lasting configurations. This sensitivity leads to the broader concept of orbital chaos. In this context, chaos does not imply randomness in the everyday sense, but rather extreme dependence on small differences. The solar system, though governed by precise laws, exhibits behavior in which tiny perturbations can alter future trajectories dramatically when extended across millions of years. Within such a framework, predicting the exact path of a single asteroid backward or forward through deep time becomes increasingly uncertain. For a body originating in the outer regions of the belt, entry into one of these unstable zones could mark the beginning of a long inward transition. It would not rush toward its destination, but would instead follow a winding evolutionary path shaped by resonances, planetary encounters, and gradual drifts. Through this intricate network of stable corridors and destabilizing gaps, stones that once circled quietly between Mars and Jupiter sometimes find their way into the inner solar system, carried along invisible highways etched into the gravitational landscape. On an airless body turning silently in sunlight, Warmth is not evenly shared. One hemisphere faces the sun and absorbs energy. Later, as rotation carries that surface into darkness, stored heat radiates back into space. This simple cycle of heating and cooling produces a faint but measurable push, a recoil created by photons leaving the surface. Known as the Yarkovsky effect, it operates with extraordinary subtlety, yet over vast durations, it can reshape an orbit. When sunlight strikes an asteroid, the absorbed energy raises the temperature of its outer layers. Because rock does not release this heat instantly, the warmest point often lags behind the point of maximum illumination. As the surface rotates into the afternoon side of its local day, it emits infrared radiation. Each escaping photon carries momentum, and together they create a gentle thrust. The direction and magnitude of this thrust depend on rotation rate, axis tilt, size, and surface composition. For a small asteroid only a few miles across, the resulting force is minuscule compared with gravitational influences. It cannot alter the path over months or centuries in any visible way. Yet over millions of years, even a tiny, persistent acceleration accumulates. The semi-major axis of the orbit can drift inward or outward by measurable distances. The process resembles a slow tide rather than a sudden shove, altering the asteroid's position gradually against the backdrop of planetary motion. Rotation direction plays a crucial role. An asteroid spinning in the same direction as its orbit around the Sun may experience a steady outward drift, slowly increasing its orbital radius. A retrograde spinner may drift inward, edging closer to the Sun over geological timescales. Surface properties matter as well. Dark, carbon-rich material absorbs more sunlight and can amplify thermal recoil compared with brighter, more reflective rock. Within the asteroid belt, this quiet effect can guide bodies toward regions of dynamical instability. An object that begins in a relatively stable zone may, over tens of millions of years, migrate into one of the resonance gaps shaped by Jupiter's influence. Once within such a region, gravitational perturbations can magnify the change. Orbital eccentricity may grow, stretching the path until it intersects that of Mars and eventually Earth. Computer models tracing asteroid populations demonstrate how this slow drift feeds larger orbital rearrangements. Without the Yarkovsky effect, many fragments would remain confined to long-lived, nearly circular orbits. Thermal forces act as a delivery mechanism, nudging bodies into gravitational corridors that redirect them inward. The combined action of sunlight and planetary gravity forms a chain of cause and consequence extending across deep time. Meteorites recovered on Earth sometimes preserve evidence of this journey. Their cosmic ray exposure ages indicate prolonged transit through interplanetary space, suggesting they were freed from parent bodies and later migrated toward Earth, crossing paths. Such migration is consistent with a gradual, thermally driven drift followed by gravitational scattering. The Chicxulub impactor, inferred to have been carbon-rich and likely modest in size before collision, would have been susceptible to these forces. Over millions of years, it may have absorbed sunlight, rotated steadily, and released heat into space, each cycle imparting a nearly imperceptible change. Through this persistent recoil, it could have shifted from a quiet orbit between Mars and Jupiter into a pathway shaped by resonances, ultimately entering the inner solar system. In the vast arithmetic of celestial mechanics, even the faint pressure of sunlight can redirect a stone, provided enough time is given for that small influence to accumulate. Some small bodies do not remain confined to the distant belt. Through gradual drift and gravitational reshaping, A portion of them enter orbits that bring them into the inner solar system, crossing or approaching the path traced by Earth. These objects are known as near-Earth objects, a category defined not by composition but by trajectory. If an asteroid or comet comes within about 1.3 astronomical units of the Sun and its orbit brings it close to Earth's orbital distance, it is placed within this group. Near-Earth objects include several dynamical classes. Some, called Atira asteroids, orbit almost entirely within Earth's path around the Sun. Others, known as Apollo asteroids, spend much of their time beyond Earth's orbit but cross it as they move along elongated trajectories. There are also Amor asteroids, which approach closely yet do not quite intersect Earth's path. Together, these categories describe a shifting population of bodies that pass through the inner solar system on timescales of thousands to millions of years. Current surveys have identified tens of thousands of such objects, ranging in size from a few meters to several kilometers across. The largest among them are catalogued carefully, their positions measured repeatedly to refine orbital predictions. Automated telescopes scan the sky each night, comparing new images to previous ones to detect faint points of light that shift against the background of stars. Once discovered, an object's orbit is calculated and updated as additional observations narrow uncertainties. Impact probability is determined by projecting these orbits forward using models that account for gravitational influences from planets and, when necessary, subtle forces such as thermal recoil. For most known near-Earth objects, the calculated likelihood of collision within the coming centuries is extremely low. The geometry of space provides vast regions through which these bodies travel without intersecting Earth at the same moment. Even for those that cross Earth's orbit, timing must align precisely for an encounter to occur. In rare cases, a newly discovered object may show a small, temporary probability of impact decades in the future. As further observations refine its path, that probability often diminishes to zero. The process illustrates how minor uncertainties in measurement can expand or contract predicted outcomes over time. Orbital calculations grow more stable as data accumulates, revealing whether an apparent risk is genuine or merely an artifact of limited information. Earth has experienced many close approaches throughout recorded history. Some small asteroids have entered the atmosphere and disintegrated, producing bright fireballs or airbursts. The event over Chelyabinsk in 2013, caused by a body roughly 20 meters wide, demonstrated how even modest objects can release significant energy without reaching the ground. Larger impacts are far less frequent, yet geological records confirm that they have occurred over millions of years. Most near-Earth objects originate from the main belt, delivered inward through resonances and thermal drift. Others arrive from farther out, fragments of comets nudged toward the Sun. Their presence serves as a reminder that Earth moves within a dynamic system where orbital paths intersect and diverge continuously. Tracking programs, supported by observatories across the globe, continue to expand the catalog. Each new entry refines our understanding of the inner solar system's architecture. Although the probability of a large impact in any given year remains low, the long arc of planetary history shows that encounters do occur. The classification and monitoring of near-Earth objects transform those encounters from unforeseeable surprises into events that can be anticipated and studied within the quiet precision of celestial mechanics. Beyond the orbit of Neptune, the Sun's light grows faint and cold, illuminating a frontier of ice and shadow. In this distant realm, far past the familiar paths of the inner planets, countless frozen bodies travel along elongated trajectories. Some reside within the Kuiper Belt, a broad disk of icy remnants left from planetary formation. Others drift in the even more distant Oort cloud, a vast spherical reservoir extending tens of thousands of astronomical units from the Sun. Here, gravity from passing stars and the gentle tide of the Milky Way exert subtle influence, shaping orbits that are measured not in years, but in tens of thousands of years. These outer populations contain objects rich in volatile compounds, including water ice, carbon dioxide ice, methane, and ammonia. When stable in the cold darkness, they remain inert, their surfaces quiet and crystalline. Yet when gravitational disturbances alter their paths, some begin long inward journeys toward the inner solar system. A passing star, even one many light years away, can slightly perturb bodies in the Oort cloud. Over time, these perturbations accumulate, nudging certain objects onto highly elongated orbits that carry them toward the Sun. As these long-period objects approach the warmer inner regions, sunlight begins to vaporize surface ices. Gas and dust stream outward, forming the luminous coma and tail characteristic of comets. The visual spectacle is a byproduct of sublimation, a transformation from solid to gas, driven by increasing temperature. Beneath the bright coma lies a nucleus composed of mixed ice and rocky material, often only a few kilometers across, but containing pristine matter from the earliest solar system. The path of such a body is dramatically different from that of most main belt asteroids. While belt asteroids follow relatively modest eccentricities and remain confined between Mars and Jupiter unless disturbed, long-period comets trace sweeping ellipses that may take thousands or millions of years to complete. Their inclinations can vary widely, some approaching from steep angles relative to the planetary plane. A single inward passage may be their only close encounter with the Sun before they are ejected again or disrupted by tidal forces. Dynamical models show that, although less common than belt-derived objects, these distant visitors can intersect Earth's orbit. Their high velocities, often exceeding those of typical asteroids, reflect the energy gained during their long descent into the Sun's gravitational well. An impact from such a body would release immense kinetic energy, amplified by its rapid approach. Yet composition provides important distinctions. Icy comets tend to contain higher proportions of volatile elements and display isotopic signatures that can differ from those of carbon-rich asteroids formed closer to the Sun. Laboratory analysis of impact, debris, and boundary layers allows scientists to compare these signatures. Oxygen and chromium isotopes, along with the abundance of certain trace metals, help differentiate between a cometary source and a main belt asteroid origin. While the evidence gathered thus far favors a carbon-rich asteroid from the outer belt for the Chicxulub impactor, the distant edge of the solar system remains a plausible alternative pathway in principle. It illustrates the variety of sources capable of sending material inward. The outer reservoirs continue to release occasional visitors, their journeys shaped by gravitational tides and stellar encounters. In the broader architecture of the solar system, both rocky asteroids and icy comets participate in a slow exchange between distant cold and inner warmth, carrying fragments of ancient history along sweeping orbits toward the Sun. In the quiet reaches of interplanetary space, small bodies fall into two broad families, similar in their size, yet distinct in their character. Asteroids tend to be built primarily of rock and metal, aggregates of silicates, iron, nickel, and in some cases, carbon-rich compounds. Many formed in the warmer regions of the early solar system, where volatile materials could not easily condense. Their interiors may be solid and monolithic, or loosely bound rubble piles held together by gravity after ancient collisions. Comets, by contrast, originate in colder environments where ices remained stable during planetary formation. Their nuclei are mixtures of frozen water, carbon dioxide, carbon monoxide, methane, and dust. In these objects, volatile compounds occupy a substantial fraction of the mass. When a comet resides far from the Sun, it remains inert and dark, much like a small asteroid. The difference becomes visible only as it approaches the inner solar system, and heat begins to release trapped gases. Ice content defines much of this contrast. Asteroids within the main belt typically contain little surface ice, though carbonaceous varieties may include hydrated minerals that hint at ancient interactions with water. Comets possess abundant volatile ices that sublimate when warmed, producing expansive comae and tails. This outgassing can alter a comet's rotation and slightly adjust its orbit, a behavior rarely observed in rocky asteroids. Orbital geometry also separates these populations. Most asteroids travel in relatively low inclination orbits near the plane defined by the planets. Their paths are modestly elliptical, shaped by the gravitational architecture between Mars and Jupiter and, when perturbed, by resonances that guide some inward. Comets arriving from the Kuiper belt or Oort cloud often display far more elongated trajectories. Their eccentricities approach unity, meaning they spend the majority of their time far from the Sun before sweeping inward briefly. Inclinations vary widely, with some comets descending from steep angles relative to the planetary plane. Speed reflects these differing origins. Main belt asteroids that evolve into Earth-crossing objects typically approach at velocities comparable to Earth's orbital speed, adding tens of kilometers per second to the encounter. Long-period comets, having fallen from great distances, can arrive with even higher relative velocities. The deeper the gravitational descent toward the Sun, the greater the kinetic energy accumulated. When such a body intersects Earth's path, the energy released upon impact scales with the square of that velocity, amplifying the effect of increased speed. Impact signatures preserve clues to these distinctions. A comet rich in volatiles may produce a plume containing higher fractions of certain light elements, while a carbon-rich asteroid leaves behind trace metal patterns consistent with chondritic material. Isotopic ratios, particularly in oxygen and chromium, provide diagnostic fingerprints. Laboratory comparisons between boundary layers in sedimentary rock and known meteorite classes help identify whether the impacting body carried more resemblance to primitive asteroids or to icy cometary nuclei. Although both classes can intersect Earth's orbit, statistical modeling suggests that most large impacts in recent geological time derive from the main asteroid belt. This reflects the steady supply generated by resonances and thermal drift. Comets contribute a smaller but significant fraction, especially during epochs of dynamical upheaval. In essence, asteroids and comets represent two expressions of early solar system material, differentiated by temperature and distance during formation. Their compositions, orbits, and velocities shape how they move through space and how they interact with planets. By reading the mineral and isotopic traces embedded within ancient layers, scientists distinguish between these origins, separating rocky fragments from icy wanderers in the long record of impacts on Earth. In laboratories where fragments no larger than dust are handled with steady hands, the story of the impact continues to unfold at the scale of atoms. The thin boundary layer, preserved in sedimentary rock, contains particles that endured extraordinary temperatures and pressures, yet within them remain subtle chemical signatures. By isolating these grains and subjecting them to precise measurements, scientists extract information that cannot be seen with the naked eye. Isotopes provide some of the clearest clues. Atoms of the same element can differ slightly in mass depending on the number of neutrons in their nuclei. These variations act like coded markers, shaped by the conditions under which the material formed. Oxygen isotopes are particularly valuable. Ratios between oxygen 16, 17, and 18 differ among meteorite classes, reflecting the distinct reservoirs present in the early solar system. When researchers analyze impact-related minerals from the boundary layer, they compare these ratios with established values measured in known meteorites. Chromium and osmium isotopes add further resolution. Certain carbonaceous chondrites display characteristic patterns in chromium 54 and osmium isotopic abundances. The extinction boundary layer reveals similar anomalies, suggesting that the impactor shared ancestry with these primitive meteorites. Such correspondence does not prove identity with a single object, yet it narrows the range of possible source regions. Mineral structures also record the violence of formation and collision. Within quartz grains, planar deformation features appear as microscopic lamellae aligned in specific orientations. These structures form only under sudden, intense shock pressures, far exceeding those generated by volcanic activity. Their presence within boundary sediments confirms the role of high-energy impact rather than gradual geological processes. Melt droplets recovered from drill cores exhibit textures consistent with rapid cooling from a liquid state, sometimes containing tiny spinel crystals formed in the plume of vaporized rock. When these mineral signatures are compared to meteorites that fall to Earth today, similarities and differences emerge. Carbon-rich chondrites recovered from deserts and Antarctic ice fields contain hydrated silicates, organics, and trace metal patterns resembling those inferred from the impact debris. Their isotopic fingerprints align closely with the anomalies detected in boundary layers. Metallic iron meteorites, on the other hand, display markedly different compositions and isotopic ratios. Such discrepancies help eliminate certain asteroid types from consideration. There are also limits to the match. Some cometary materials collected by space missions show isotopic signatures that differ from those observed in the extinction layer. In particular, certain nitrogen and hydrogen isotope ratios found in cometary samples diverge from the boundary values. These differences argue against a purely icy, long-period comet as the source of the Chicxulub impactor. The absence of strong signatures associated with volatile, rich nuclei strengthens the interpretation that the object was more consistent with a carbonaceous asteroid. Each analytical technique refines the picture without claiming absolute certainty. Contamination, alteration through heat, and mixing with terrestrial material introduce complexity. Yet when multiple independent measurements converge on similar conclusions, confidence grows. Isotopic ratios align with primitive outer belt material. Mineral shock features confirm impact conditions. Trace element abundances resemble known carbon-rich meteorites rather than metallic or purely rocky classes. Through these comparisons, the debris becomes more than a remnant of catastrophe. It becomes a fragment of a larger population, chemically tied to ancient bodies that still circle the sun. The thin layer in Earth's stratigraphy holds within it echoes of formation environments, billions of years old. preserved in isotopes and crystal lattices that bridge laboratory instruments and the distant regions where the impactor first assembled. Among the many classes of meteorites stored in climate-controlled drawers and research collections, a small fraction stand apart for their darkness and fragility. These are carbonaceous chondrites, primitive fragments that preserve some of the earliest solid material formed in the solar system. Their surfaces are often black or deep gray, rich in carbon compounds and fine-grained minerals that have changed little since the era when dust first coalesced around the young sun. Carbonaceous chondrites contain tiny spherical inclusions called chondrules, once molten droplets that cooled rapidly in the protoplanetary disk. Surrounding them is a matrix dense with organic molecules, hydrated silicates, and volatile bearing compounds. Some specimens hold amino acids and complex carbon chains, assembled through chemical processes that preceded the formation of planets. These meteorites are delicate, easily altered by moisture and heat, which is why many are recovered from arid deserts or Antarctic ice, environments that slow their transformation. The presence of carbon-rich material in the extinction boundary layer suggests that the Chicxulub impactor shared characteristics with this rare group. Elevated concentrations of certain trace elements, alongside isotopic patterns consistent with carbonaceous chondrites, strengthen this connection. While not every detail matches perfectly, the overall chemical signature points toward a primitive asteroid rather than a metallic body or volatile-dominated comet. This association narrows the range of likely origin zones. Carbonaceous asteroids are more common in the outer portion of the main belt, where lower temperatures during formation allowed water and carbon compounds to remain stable within accreting bodies. In contrast, asteroids closer to the Sun tend to be depleted in such volatiles. By matching boundary debris to carbon-rich meteorites, scientists constrain the impactor's birthplace to regions beyond the warmer inner belt. Comparison relies on meticulous laboratory work. Samples from the boundary layer are dissolved, vaporized, or analyzed with ion beams to measure elemental and isotopic abundances at parts per billion levels. Meteorites in curated collections undergo identical procedures. By aligning methods and calibrating instruments carefully, researchers ensure that results can be compared directly. Patterns in oxygen isotopes, chromium anomalies, and ratios of platinum group elements provide overlapping lines of evidence. No single measurement establishes certainty. Instead, confidence grows through convergence. When oxygen isotopes from the boundary layer cluster near values typical of carbonaceous chondrites, and chromium isotopes show similar deviations, and trace metal abundances align within expected ranges, the case strengthens. Discrepancies are evaluated closely, considering the effects of extreme heating during impact and mixing with terrestrial rock. Carbonaceous material also carries implications about the broader history of the solar system. These primitive bodies have remained relatively unaltered since their formation, preserving chemical conditions from more than 4 billion years ago. If the Chicxulub impactor belonged to this lineage, then the stone that reshaped Earth's biosphere originated in a region where ancient organic compounds had survived since the earliest epochs. Through careful comparison of microscopic grains and isotope ratios, scientists refine the portrait of the impactor. The carbonaceous clue does not point to a single named asteroid, yet it anchors the investigation within a defined population of primitive outer belt bodies. In this way, chemistry acts as a compass, guiding attention toward a specific domain of the solar system where dark, carbon-rich fragments continue to circle the Sun in quiet persistence. When the distribution of asteroids is plotted with precision, certain distances from the Sun appear curiously underpopulated. These narrow bands, first identified in the 19th century by Daniel Kirkwood interrupt the otherwise continuous spread of orbital paths within the main belt. They are known as Kirkwood gaps, and their existence reflects a quiet but persistent gravitational dialogue between Jupiter and the smaller bodies sharing the solar system. Each gap corresponds to a simple numerical relationship between the orbital period of an asteroid and that of Jupiter. At one location, an asteroid might complete exactly 3 orbits for every one orbit of Jupiter. At another, the ratio could be 5 to 2 or 7 to 3. These resonances seem harmless at first glance, merely neat fractions written into celestial motion. Yet the repetition of gravitational alignment creates cumulative effects. When an asteroid returns to the same relative configuration with Jupiter again and again, the planet's gravitational pull is applied rhythmically, like a steady pulse. Over thousands, then millions of cycles, these periodic tugs gradually alter the asteroid's trajectory. Its orbit becomes more eccentric, stretching from nearly circular to noticeably elongated. The semi-major axis may shift slightly, but the more consequential change is in the shape of the path. As eccentricity increases, the asteroid begins to cross the orbits of neighboring planets. What was once confined comfortably between Mars and Jupiter can transform into a path that intersects the inner solar system. The gaps themselves represent zones where long-term stability is scarce. Asteroids that wander into these resonant corridors do not remain there indefinitely. They are either driven inward, scattered outward, or relocated onto new paths that avoid the precise resonance. Jupiter, through these gravitational harmonics, effectively clears specific orbital zones. The result is a belt with distinct missing bands, visible when plotted against distance. Objects originating near these resonances are statistically more likely to evolve into Earth-crossing orbits. Numerical simulations tracing millions of hypothetical particles show that fragments placed within certain Kirkwood gaps migrate toward the inner planets more readily than those in stable regions. The process is not immediate. It unfolds over tens of millions of years, guided by subtle gravitational exchanges and occasionally amplified by close encounters with Mars. These dynamics create probability pathways through which material is funneled from the belt toward Earth's neighborhood. The pathways are not fixed tracks, but regions of increased likelihood. A fragment entering one of these zones experiences a higher chance of orbital evolution that intersects Earth's path. Many such objects will still miss entirely, passing safely through the inner solar system before being diverted again. Yet the statistical bias remains measurable. When considering the Chicxulub impactor, the significance of these gaps becomes clear. A carbon-rich asteroid residing in the outer portion of the belt could have drifted slowly, influenced by thermal forces until it entered a resonant region. There, repeated gravitational interactions with Jupiter might have amplified its eccentricity, placing it onto a trajectory that crossed Earth's orbit. The final encounter would still depend on timing, alignment, and chance, yet the resonance would have served as a gateway from long-term stability to potential impact. In this way, the Kirkwood gaps function as quiet architects of planetary risk. They do not launch stones deliberately, nor do they guarantee collision. Instead, they shape the statistical landscape of motion, creating corridors where probabilities shift. Within the broad expanse of the asteroid belt, these empty bands mark regions where gravity's rhythm slowly reshapes orbits, guiding select fragments onto inward journeys that may, under rare alignment, intersect with Earth. Geologic time does not unfold with a steady rhythm of catastrophe. Millions of years can pass in relative calm, then a single collision alters the course of life. The question of timing lingers in the background of every impact study, not as a matter of fate but of probability. Why did a large object intersect Earth's path 66 million years ago rather than 10 million years earlier or later? Within the mechanics of the solar system, timing emerges from the interplay between random encounters and slow orbital cycles. An asteroid delivered inward from the main belt follows a path shaped by resonances, thermal drift, and planetary perturbations. Once its orbit crosses Earth's, a collision remains far from inevitable. Space is vast, and Earth occupies only a small fraction of any given orbital corridor. Even when paths intersect geometrically, the two bodies must arrive at the same point at precisely the same moment. Most crossings result only in close passes, the asteroid continuing onward, Earth continuing around the Sun. Statistical modeling provides insight into how often such alignments occur. Based on crater counts on Earth, the Moon, and other terrestrial planets, scientists estimate that objects roughly 6 miles wide strike Earth on timescales of tens to hundreds of millions of years. The exact interval fluctuates depending on the evolving population of near-Earth objects and the dynamical state of the asteroid belt. The Chicxulub event fits within these broad expectations, rare on human scales yet not anomalous across geological history. Earth's own surface preserves a partial record of these encounters. Erosion, tectonic activity, and sedimentation erase many craters over time, but dozens of confirmed impact structures remain. Some are small, measuring only a few kilometers across. Others, like the vast basin hidden beneath the Yucatán Peninsula, reach over 100 miles in diameter. Lunar craters, preserved in an environment without weather or plate tectonics, provide a clearer cumulative record. Their density suggests that impacts were far more frequent in the early solar system and have declined as debris populations diminished. The late heavy bombardment period, more than 3 billion years ago, marked an era of intensified impacts likely triggered by shifts in planetary orbits. Since then, the frequency of large collisions has decreased, though never to zero. Asteroids continue to drift through resonant zones, and comets still descend from distant reservoirs. The overall rate reflects the gradual clearing of leftover planetesimals rather than a clock set to fixed intervals. Randomness plays a decisive role within this structured environment. Even if the supply of Earth-crossing asteroids remains relatively steady, the moment of impact depends on specific orbital phases. Small differences in initial conditions can shift encounter times by millions of years. Computer simulations tracing backward trajectories demonstrate how chaotic evolution limits precise prediction over deep time. The Chicxulub impact therefore did not occur because a cycle reached completion at 66 million years. It resulted from a confluence of long-term drift, resonance-driven orbital evolution, and the chance alignment of two bodies sharing intersecting paths. On geological scales, such alignments are expected to occur occasionally. They cluster neither in strict periodicity nor in complete isolation, but within probability ranges shaped by the dynamical architecture of the solar system. In Earth's layered history, the boundary marking that collision represents one entry within a longer sequence. It stands out because of its biological consequences, yet its timing reflects the broader statistical behavior of small bodies moving through space, governed by gravity and influenced by minute forces that accumulate across immense spans of time. Long before the boundary that separates the age of dinosaurs from the world that followed, Earth had already endured episodes of profound biological loss. The fossil record preserves several mass extinctions, intervals when biodiversity declined sharply across oceans and continents. Not all of these events were caused by impacts, yet collisions form part of the broader tapestry of planetary disruption that has shaped life's history. Large craters scattered across Earth's crust attest to ancient encounters. The Vredefort structure in South Africa, more than 2 billion years old, records an impact far larger than the basin beneath the Yucatan. In Canada, the Sudbury impact left behind a vast geological formation and rich mineral deposits. These ancient scars formed in eras when life was limited to oceans and microbial ecosystems. Their biological consequences remain difficult to reconstruct, yet they demonstrate that Earth has been struck by sizable bodies many times. Compared to the early solar system, however, the frequency of giant impacts declined steadily. The period known as the Late Heavy Bombardment delivered numerous collisions during the first several 100 million years after planetary formation. Since then, the clearing of debris and the stabilizing influence of planetary orbits have reduced the rate dramatically. On the scale of hundreds of millions of years, impacts capable of producing craters over 100 miles wide are rare, yet they are not singular. The extinction at the end of the Cretaceous stands out because of its ecological context. Other mass extinctions, such as the end Permian event around 250 million years ago, appear to have been driven primarily by extensive volcanic activity and climate change rather than impact alone. The Chicxulub collision occurred in a world already experiencing environmental shifts. Volcanic eruptions associated with the Deccan traps were releasing vast quantities of gases into the atmosphere, altering climate patterns and ocean chemistry. When the impact occurred, ecosystems were therefore not in perfect equilibrium. Food webs on land and in the sea were interconnected in complex ways, and many species occupied narrow ecological niches. The sudden reduction in sunlight caused by high-altitude aerosols disrupted photosynthesis, collapsing primary productivity. Organisms dependent on stable temperature and abundant plant growth proved particularly vulnerable. In contrast, smaller animals capable of burrowing, scavenging, or enduring extended periods without food had greater chances of survival. The scale of biological loss was shaped not only by the energy of the collision, but by the environmental sensitivity of the moment. Continental arrangements, sea levels, and atmospheric composition all influence how an ecosystem responds to rapid disturbance. During the late Cretaceous, widespread shallow seas and diverse plankton communities formed the foundation of marine food chains. When sunlight diminished, these systems faltered quickly, transmitting stress upward through predators and large reptiles. Giant impacts are therefore uncommon, but not unprecedented in Earth's chronology. What distinguishes the event 66 million years ago is the convergence of impact energy with a biosphere structured in a way that magnified consequences. Similar-sized collisions in earlier eras may have produced regional devastation without triggering global collapse, depending on prevailing environmental conditions. In the layered record of Earth's past, impact craters and extinction horizons mark moments when cosmic processes intersected with biological evolution. The Chicxulub event was part of this continuum, extraordinary in its ecological effect yet embedded within a longer history of planetary encounters. Its uniqueness lies less in the physical act of collision and more in the state of the world it struck, a world poised at a delicate balance between resilience and transformation. In quiet rooms filled with processors rather than rock samples, the story is rewound using mathematics instead of sediment. Astronomers and dynamicists take the known laws of gravity, the measured positions of planets, and the present structure of the asteroid belt, then let virtual fragments move across simulated millions of years. These computer models do not replay a single guaranteed history, but generate vast ensembles of possible paths, each consistent with physical principles and measured constraints. The Chicxulub impactor itself cannot be followed backward directly, its fragments long dispersed or buried. Instead, scientists begin with populations of carbon-rich asteroids in the outer main belt, assigning them slightly varied starting positions and velocities. They then allow thermal forces, resonances, and planetary perturbations to act across extended timescales. By tracking how many of these modeled bodies evolve into Earth-crossing orbits, researchers identify the most probable delivery routes. Resonance zones linked to Jupiter receive particular attention. Simulations demonstrate that objects drifting into specific Kirkwood gaps experience accelerated growth in orbital eccentricity. From there, close encounters with Mars and Earth refine trajectories further, sometimes stabilizing them temporarily as near-Earth asteroids before eventual collision or ejection. The frequency with which modeled bodies from each belt region reach Earth provides a statistical map of likely source zones. Comparative analysis between inner belt and outer belt populations adds refinement. Bodies originating in the inner belt, typically more silicate-rich, display different spectral and compositional signatures than the carbonaceous asteroids inferred from the boundary layer. When models show that outer belt fragments both match the chemistry and possess efficient dynamical pathways toward Earth, the case strengthens. Conversely, simulations of long-period comet influx suggest lower probabilities for impacts of the required size within the relevant geological window. Backward trajectory modeling must also account for uncertainty. Small variations in initial conditions produce diverging outcomes over tens of millions of years, a hallmark of chaotic gravitational systems. To address this, researchers run thousands or even millions of iterations, altering parameters slightly each time. The resulting distribution of outcomes forms a probability landscape rather than a single deterministic solution. Within this landscape, certain regions of the asteroid belt emerge as statistically favored birthplaces. Carbon-rich bodies from the outer main belt, particularly those near strong resonances, appear capable of reaching Earth-crossing orbits on timescales compatible with the age of the impact. Confidence levels are expressed not as absolute declarations, but as relative likelihoods, weighted by chemical consistency and dynamical efficiency. Even with advanced computation, margins of uncertainty remain. Planetary positions can be reconstructed with high precision over tens of millions of years, yet, beyond that horizon, chaotic divergence increases. Thermal forces like the Yarkovsky effect introduce additional variability, sensitive to rotation, state, and surface properties that cannot be known for a vanished object. Models therefore provide ranges and probabilities rather than precise backward paths. Through these simulations, the narrative narrows from the entire solar system to defined corridors within the asteroid belt. The final orbit that intersected Earth represents the endpoint of countless incremental adjustments, each governed by gravity and time. While no model can recover the exact sequence of events for a single stone, the convergence of chemical evidence and dynamical probability outlines a coherent scenario. Within that framework, the likely source region becomes less a mystery of chance and more a statistically supported origin embedded within the architecture of the main belt. Long before the present architecture of the planets settled into familiar spacing, the solar system moved through a period of quiet rearrangement. The giant planets did not necessarily form exactly where they now reside. Models of early solar evolution suggest that Jupiter, Saturn, Uranus, and Neptune may have shifted their positions during the first several hundred million years, responding to interactions with the remaining disk of planetesimals that surrounded them. In these scenarios, often grouped under what is called the Nice model, the outer planets began in a more compact configuration. Beyond them extended a massive disk of icy bodies, remnants of formation that had not yet been cleared. As Jupiter and Saturn gradually interacted with this disk, exchanging angular momentum through countless gravitational encounters, their orbits adjusted. A subtle resonance between Jupiter and Saturn altered the stability of the entire outer system, triggering a period of migration. When giant planets migrate, even by modest distances, the gravitational landscape changes dramatically. Resonance zones sweep across the asteroid belt and beyond, destabilizing objects that had previously occupied long-lived paths. Planetesimals can be scattered inward toward the terrestrial planets or outward into distant reservoirs, such as the Oort cloud. Numerical simulations indicate that this migratory phase likely contributed to a spike in impact rates known as the late heavy bombardment, reshaping surfaces across the moon and inner planets. Although this era occurred billions of years before the Chicxulub event, its effects endured. The redistribution of small bodies during planetary migration did not produce a perfectly stable configuration afterward. Instead, it left behind populations arranged within a dynamically complex structure. Certain regions of the asteroid belt remained marginally stable, while others carried the imprint of past resonances that had swept through them. Even long after the major migrations subsided, these altered distributions influenced the likelihood of future impacts. The belt that survived was not simply a quiet leftover, but a population filtered by early chaos. Families of asteroids created by collisions evolved within this environment, some residing near persistent resonance gaps that continued to channel fragments inward. The architecture shaped during early instability therefore defined the pathways available hundreds of millions of years later. In addition to reshaping the main belt, planetary migration is thought to have populated distant cometary reservoirs. Icy bodies scattered outward during the chaotic phase now occupy the Kuiper belt and Oort cloud. From time to time, gravitational perturbations can redirect a fraction of them inward, maintaining a slow exchange between distant cold and inner warmth. The key insight is that the solar system's current structure is the outcome of an early period of dynamical adjustment rather than a static inheritance from formation. The positions of the giant planets determine the location of resonances, and those resonances regulate how small bodies drift and evolve. A modest outward or inward shift in Jupiter's orbit billions of years ago would have altered which regions of the asteroid belt became stable sanctuaries and which became unstable corridors. By the time Earth was home to forests and dinosaurs, the dramatic migrations had long since ended. Yet the framework they created persisted, guiding the slow evolution of asteroids through resonant gaps and thermal drift. The stone that would eventually intersect Earth's path moved within a gravitational system shaped by ancient instability, its trajectory influenced by patterns established in the solar system's youth and preserved across vast spans of time. Long before it ever approached the warmth of Earth's orbit, the asteroid moved in quiet obscurity among countless others, tracing a path between Mars and Jupiter that seemed unremarkable. For millions of years, it followed a stable ellipse, one among many, its rotation steady, its surface absorbing and re-emitting sunlight as it circled the sun in darkness punctuated by distant light. No sudden event marked the beginning of its inward drift. The change emerged gradually, shaped by forces too small to perceive in a single lifetime. Thermal recoil altered its semi-major axis by fractions of a kilometer at a time, gravitational resonances waited like invisible thresholds. When the asteroid's slow migration carried it into one of these regions, repeated tugs from Jupiter subtly stretched its orbit. Eccentricity increased, transforming a nearly circular path into a more elongated ellipse. With each revolution, the asteroid ventured slightly closer to the Sun at perihelion and slightly farther outward at aphelion, its trajectory evolving through patient accumulation rather than abrupt motion. As the orbit grew more elongated, it began to intersect the path of Mars. The first close passes did not result in collision. Instead, they produced modest gravitational exchanges. Mars shifted the asteroid's velocity by small increments, altering inclination or rotating the line of apsides. Each encounter introduced a new variation, unpredictable in detail, yet constrained by physical law. Some trajectories stabilized temporarily after these interactions, lingering in transitional orbits that crossed Mars but remained distant from Earth. Over extended spans of time, additional adjustments carried the asteroid farther inward. The orbit now crossed Earth's path as well. Yet even with geometric intersection, impact remained unlikely. The asteroid and Earth could pass through the same region of space at different times, separated by hours or even minutes that in orbital mechanics translate to thousands of kilometers of distance. Close approaches to Earth would have occurred long before the final collision. During these encounters, Earth's gravity slightly deflected the asteroid's course, refining its orbital elements. Numerical studies of similar bodies show that such flybys can lower perihelion distance incrementally, tightening the crossing angle. Each pass represented a potential end, yet also a continuation, the asteroid departing again on an altered ellipse. The long journey through near-Earth space likely lasted hundreds of thousands to a few million years. In that interval, the asteroid oscillated between relative stability and heightened risk. Small perturbations accumulated from planetary encounters and solar radiation, narrowing the range of possible future paths. The system remained sensitive to initial conditions, so that minor differences could produce divergent futures. Eventually, orbital phases aligned. Earth arrived at a point in its path at the same moment the asteroid reached its descending node. The crossing that had occurred countless times before, without consequence, now coincided in time and space. The final alignment was not marked by warning or signal visible across the solar system. It was simply the outcome of intersecting trajectories shaped by gravity and drift. The millions of years preceding that moment formed a continuous chain of incremental adjustments. No single force directed the asteroid toward Earth. Instead, a succession of small influences, each nearly negligible on its own, combined to guide it from a quiet orbit in the outer belt into a fleeting intersection with a planet. In the vast arithmetic of celestial motion, the long journey ended when two ellipses occupied the same coordinates at the same instant, closing a path that had unfolded across deep time. An orbit can intersect another for ages without consequence. Two ellipses drawn around the Sun may cross at defined nodes, yet remain separated by distance in time. For long stretches, the asteroid's path overlapped Earth's orbital corridor in geometry alone. Each year, it would pass through the same region of space. But hours before or hours after Earth had moved beyond that point, the crossing existed as potential rather than event. In celestial mechanics, inevitability is not declared by intersection alone. A body becomes hazardous only when spatial alignment converges with temporal alignment. The asteroid that would form the Chicxulub crater had likely crossed Earth's orbit many times before the final encounter. Each revolution offered an opportunity, yet most ended as near misses, the planet and the stones separated by thousands or millions of kilometers. Statistical modeling of near Earth objects reveals how common these harmless crossings are. For every large impact, there are countless passages in which Earth and asteroid share proximity in orbital space without occupying the same coordinates simultaneously. Gravitational focusing increases the effective collision cross-section slightly, bending an asteroid's path inward during close approaches. Even so, the fraction of crossing trajectories that culminate in impact remains small. The majority continue onward, altered but intact, perhaps returning again centuries or millennia later. The odds depend on orbital inclination, eccentricity, and relative velocity. A shallow crossing angle may permit multiple close approaches before a decisive outcome. Slight gravitational deflections during each flyby can adjust the timing of subsequent returns, gradually refining the alignment. In some cases, repeated interactions create what dynamicists call keyholes, narrow regions of space during a close pass that, if entered, set up a future impact on a later orbit. The asteroid passes through such a gravitational aperture, and the mathematics of its next return becomes constrained. For the Chicxulub impactor, a sequence of prior encounters may have shifted its orbit incrementally until the geometry tightened. Each close approach modified the longitude of ascending node or altered the argument of perihelion by small degrees. Over thousands of revolutions, these variations accumulated. The margin between miss and strike narrowed, not through intent, but through the patient arithmetic of gravity. Eventually, the timing synchronized. Earth arrived at the crossing point just as the asteroid descended through the plane of its orbit. The relative velocity, amplified by the inward fall toward the Sun, ensured that once within Earth's gravitational sphere of influence, escape was no longer possible. Gravitational focusing increased the effective size of Earth in that final approach, bending the trajectory enough to guarantee contact. What distinguished this crossing from the many before it was not a dramatic change in physical law, but a precise alignment in phase. Orbital elements that had been evolving gradually reached a configuration where the difference in arrival time shrank to zero. The probability inherent in millions of prior crossings resolved into certainty at a single moment. In that instant, potential became outcome. The asteroid's long sequence of near misses ended as gravity completed its work. The inevitability was statistical rather than fated, emerging from repeated opportunities and incremental adjustments. Within a system governed by predictable laws yet sensitive to small perturbations, one crossing among many aligned perfectly, closing a chain of motion that had unfolded across millions of years. In the aftermath of certainty, uncertainty remains. The crater exists, the boundary layer circles the globe, and isotopic signatures point toward a carbon-rich asteroid. Yet, within these converging lines of evidence, there are edges where the record fades. Geological archives are not perfect transcripts. They preserve fragments, compress time, and erase details through heat, pressure, erosion, and plate motion. The Chicxulub structure itself lies buried beneath sediment and water, accessible only through drill cores and geophysical imaging. Much of the original ejecta blanket has been reworked by wind, water, and tectonic shifts over millions of years. Minerals that once carried delicate information were melted, altered, or mixed with terrestrial material during the extreme conditions of impact. This limits the precision with which scientists can reconstruct the exact composition and internal structure of the original body. Some uncertainties arise from what was lost at the moment of collision. The asteroid vaporized upon impact, its material dispersed into a plume that mixed with target rock and atmospheric gases. Only trace quantities survived in recognizable form. The bulk of the object's interior structure, whether monolithic or loosely aggregated, remains unknowable. Likewise, the precise angle of impact and its subtle variations influence modeling outcomes. Although current estimates constrain the angle within a plausible range, small differences affect interpretations of ejecta distribution and environmental consequences. Competing interpretations continue to refine the narrative. While the impact is widely accepted as the primary driver of the end Cretaceous mass extinction, discussions remain regarding the interaction between the collision and contemporaneous volcanic activity. Some researchers emphasize the role of sulfur and aerosols injected by the impact into a climate system already influenced by greenhouse gases from large-scale eruptions. Others explore whether certain ecosystems had begun declining before the collision, interpreting fossil patterns with nuanced debate. The origin question itself, though narrowed by chemistry and dynamics, retains margins of doubt. Carbonaceous signatures strongly suggest an outer main belt source, yet the exact parent body remains unidentified. Models of orbital evolution depend on assumptions about rotation rates, surface properties, and ancient planetary positions, each carrying small uncertainties that compound over deep time. Chaotic behavior in gravitational systems limits the ability to trace a single object backward with absolute precision. Science evolves because new tools expand resolution. Advances in isotopic measurement allow detection of subtler anomalies than were possible decades ago. Space missions, returning samples from asteroids, provide direct comparisons between known bodies and impact debris. Improved computational power refines dynamical simulations, testing scenarios that were once computationally inaccessible. As each method improves, interpretations adjust accordingly. Uncertainty in this context does not weaken the overall framework. Instead, it defines the boundaries within which confidence operates. The broad outline remains robust. A carbon-rich asteroid migrated inward and collided with Earth 66 million years ago. Within that outline, finer details continue to be explored and occasionally revised. Earth's deep history is preserved imperfectly, filtered through geological processes and interpreted through evolving techniques. The story of the Chicxulub impact reflects both the strength and the limits of this record. It demonstrates how converging evidence can illuminate events from distant epochs, while also reminding us that every reconstruction carries residual gaps where fragments have been erased or transformed beyond recognition. Across the dark between planets, countless bodies still follow their ancient paths, most unnoticed, some carefully tracked. The sky that once delivered catastrophe is now surveyed each night by networks of telescopes that sweep methodically from horizon to horizon. Charged, coupled devices register faint points of light shifting subtly against the fixed stars, their motion betraying proximity. From mountaintops and desert plains, observatories catalog these movements, calculating preliminary orbits within hours of detection. Modern surveys, such as wide-field optical programs and infrared space telescopes, have transformed awareness. Objects that would once have passed unseen are now logged into databases, their trajectories refined through repeated observation. Automated systems compare new detections against existing catalogs, linking observations across nights to determine whether a dot of light is a known asteroid or a newly discovered near-Earth object. Over time, uncertainties shrink as additional measurements constrain eccentricity, inclination, and orbital period. Among the many thousands identified, only a small fraction are large enough to cause global devastation. Statistical assessments suggest that objects comparable in size to the Chicxulub impactor are rare on human timescales, with recurrence intervals measured in tens of millions of years. Smaller bodies, capable of regional damage, are more frequent yet still uncommon within a single century. Impact probability calculations incorporate current orbital solutions, projecting trajectories forward while accounting for gravitational perturbations and subtle forces such as thermal radiation effects. Planetary defense has emerged as a coordinated scientific effort rather than a speculative concept. International collaborations share data openly, updating risk assessments as new observations refine paths. When a newly discovered object shows a non-zero probability of impact decades into the future, continued monitoring typically reduces uncertainty, often eliminating the risk entirely. This process illustrates how precision grows with time, transforming initial ambiguity into clearer outcomes. Space missions have begun to test active deflection strategies. A recent kinetic impact experiment demonstrated that altering an asteroid's orbit, even slightly, is feasible with present technology. By colliding a spacecraft with a small target in a controlled environment, scientists measured a measurable change in orbital period. Though the tested body posed no threat, the experiment provided empirical confirmation that momentum transfer can adjust trajectories when applied years or decades before a predicted encounter. Other concepts remain under study, including gravity tractors that would hover near an asteroid and gradually tug it off course, or surface modifications that change how sunlight re-radiates from the object, subtly altering its long-term drift. These strategies depend on early detection, since even a minor velocity change applied far in advance can translate into a large positional shift over time. The catalog of known large near-Earth objects continues to grow. Many have been characterized in size and composition through radar imaging and spectral analysis. Some follow orbits that bring them close to Earth periodically, yet none currently identified presents a high probability of impact within the foreseeable future. Continued surveys aim to identify at least 90% of objects larger than 1 kilometer in diameter, reducing the likelihood of surprise from bodies of that scale. The possibility of another giant impact cannot be eliminated within a dynamic solar system. Yet, unlike the distant past, the present era includes awareness and preparation. The same gravitational mechanics that once guided a wandering asteroid toward Earth now operate within a framework of observation and response where faint moving lights are recognized, measured, and understood long before alignment can turn crossing paths into collision. History can pivot on an instant so brief it would vanish within a heartbeat, yet its consequences stretch across millions of years. The impact that closed the age of dinosaurs did not merely end lineages, it opened ecological space. In the quiet that followed devastation, entire food webs unraveled and then slowly rewove themselves into new patterns. Before that moment, mammals existed largely in the shadows. They were small, nocturnal, often burrowing or climbing in niches where larger reptiles did not dominate. Their diversity was modest compared with the towering herbivores and apex predators that shaped terrestrial ecosystems. When the impact altered climate, darkened skies, and collapsed primary productivity, many of the largest animals vanished. The extinction was selective yet widespread, sparing some groups while erasing others. This sudden absence created an ecological reset. Forest canopies changed plant communities reorganized, and oceanic food chains rebalanced around surviving species. In the wake of disappearance, vacant niches waited. Mammals diversified rapidly in the Paleogene period, evolving into herbivores, carnivores, swimmers, and gliders. Body sizes expanded from the scale of shrews to creatures rivaling the mass of former reptilian giants. Within a few million years, mammals occupied roles once held by dinosaurs. The transformation illustrates how contingent evolution can be. Had the asteroid missed, dominant reptilian clades might have continued to constrain mammalian expansion. Instead, adaptive radiations unfolded along newly available pathways. Primates eventually emerged within forested environments shaped by these post-impact dynamics, setting the stage for a lineage that would one day reflect on deep time itself. The fragility lies not only in biological outcomes, but in timing. For tens of millions of years before the collision, complex ecosystems had evolved through gradual climatic shifts and tectonic change. A single external disturbance compressed evolutionary turnover into a geologically abrupt transition. Species that had thrived for millions of years encountered conditions to which they could not adapt quickly enough. Others, by chance or by ecological flexibility, endured. Fossil records reveal this delicate threshold. In sedimentary layers straddling the boundary, abundant and diverse faunas give way to reduced assemblages dominated by survivors. Recovery proceeded unevenly across regions and environments, influenced by latitude, habitat, and existing diversity. Some lineages rebounded swiftly, while others left no descendants at all. The difference between extinction and persistence often depended on traits such as body size, metabolic demands, and dietary breadth. Earth's history contains many such inflection points, though few so dramatic. The Chicxulub impact stands as a reminder that planetary processes and cosmic events intersect. Evolution does not unfold in isolation from celestial mechanics. Instead, it responds to external perturbations, adapting within constraints imposed by environment and chance. The thin line between survival and extinction is written in geological strata as clearly as in genetic inheritance. A few degrees of cooling, a brief interval of darkness, or a disruption of food chains can tilt the balance. The rise of mammals, and eventually humans, traces back through this narrow passage shaped by impact. In contemplating this fragility, the continuity of life appears both resilient and precarious. Lineages persist across cataclysms, yet dominant groups can disappear in moments. The Earth retains scars of transformation, and within those scars, the conditions for future diversity emerge. Evolution advances not as a steady ascent, but as a sequence of expansions and contractions, sometimes guided by forces that originate far beyond the planet itself. Probability in the cosmos unfolds across spans so vast that human intuition falters. Catastrophic impacts capable of reshaping the biosphere are neither common nor impossibly rare. They occupy a statistical middle ground measured in tens of millions of years. Over the age of Earth, such events have occurred more than once, yet they are separated by intervals long enough for ecosystems to flourish, diversify, and stabilize between upheavals. During the early solar system, collisions were frequent and violent. The planets assembled through repeated impacts, their surfaces molten and unstable. Small bodies swarmed in great numbers, and gravitational interactions among migrating giant planets stirred debris into chaotic trajectories. In that formative era, Earth endured bombardment far more intense than anything experienced in the last few 100 million years. The crust recorded scars that have since been erased by tectonics and erosion, but lunar surfaces preserve the density of craters as a reminder of that restless epoch. Compared with those beginnings, the modern solar system is quieter. Many unstable populations have been depleted through collisions or ejection. Orbital resonances have sculpted debris into more predictable belts and families. The average rate of large impacts declined as the reservoir of potential impactors diminished. Earth now resides in a comparatively stable interval where global extinction level collisions are infrequent on geological timescales. Yet stability does not mean immunity. The architecture of the solar system, shaped by gravity and long-term evolution, continues to allow occasional inward migration of objects from distant reservoirs. Jupiter plays a dual role in this arrangement. Its immense mass acts as a barrier that captures or redirects many comets and asteroids before they approach the inner planets. At the same time, resonances linked to its orbit can perturb certain regions of the asteroid belt, nudging bodies onto Earth crossing paths. In this way, Jupiter functions both as shield and instigator, reducing some risks while contributing to others. The probability of a life-ending impact at any given moment remains small. Risk accumulates gradually over immense spans, rising as time passes without such an event. Statistical models describe this as a Poisson process, where the likelihood of occurrence within a given interval can be estimated but not precisely forecasted. There is no cosmic schedule marking when the next large collision must occur. Instead, each epoch carries its own fraction of possibility. Timing, therefore, retains an element of randomness. The Chicxulub impact occurred 66 million years ago, not because that moment held unique cosmic significance, but because orbital paths aligned then rather than earlier or later. Had the same object arrived a few million years before or after, evolutionary trajectories might have diverged dramatically. The contingency underscores how deeply biological history intertwines with celestial mechanics. Cosmic coincidence is not mystical. It arises from the interplay between deterministic laws and sensitive dependence on initial conditions. Gravity governs every orbit with precision, yet minute differences in position or velocity can amplify over millions of years. From these subtle variations emerges the occasional intersection of paths that reshapes a planet's surface and its living communities. Earth's relative safety today reflects the gradual calming of a once turbulent system. Still, the background probability persists, woven into the architecture of planetary motion. Life evolves within this framework of low but enduring risk. Its continuity shaped not only by internal resilience, but also by events that originate far beyond the atmosphere. Long before it touched Earth, the asteroid that ended the Cretaceous began as part of a far older story, embedded within a population of primitive bodies circling between Mars and Jupiter. Its birthplace, according to the strongest current evidence, lies in the outer portion of the main asteroid belt, within a region rich in carbonaceous material that has remained relatively unaltered since the solar system's formation. Geochemical clues provide the foundation for this conclusion. The thin boundary layer, preserved in sediments worldwide, contains elevated levels of iridium and other platinum group elements consistent with a specific class of meteorites known as carbonaceous chondrites. Within this class, certain subtypes display isotopic ratios and trace element patterns that closely align with measurements taken from impact-related material. Chromium isotopes, in particular, serve as a diagnostic marker, distinguishing carbonaceous sources from ordinary stony meteorites. When laboratory analyses compare these isotopic fingerprints, The match points toward a primitive, carbon-rich asteroid rather than an icy, long-period comet or a differentiated rocky body. Mineralogical structures within the debris reinforce this interpretation. Tiny inclusions and altered silicates resemble those found in samples linked to outer main belt asteroids. Spectroscopic observations of present-day asteroids in that region reveal reflectance patterns consistent with similar carbon-bearing compounds. These observations bridge laboratory chemistry on Earth with remote sensing data gathered from orbiting telescopes. Dynamical modeling adds another layer of support. Simulations tracing the likely pathways of large near-Earth objects show that fragments originating in the outer asteroid belt have a statistically significant probability of entering resonances that deliver them inward. Regions associated with specific gravitational gaps provide efficient transfer routes. Over millions of years, bodies from these zones can migrate onto Earth, crossing trajectories with a frequency compatible with the timing of the Chicxulub event. This alignment between chemical evidence and orbital dynamics strengthens the case for an outer belt origin. Researchers lean toward this source region because it satisfies multiple independent lines of inquiry. The composition of the impactor matches known materials from that part of the belt. The dynamical environment offers plausible pathways to Earth. The size distribution of outer belt families includes objects large enough to produce a crater exceeding 100 miles in diameter. The convergence of these factors forms a coherent narrative supported by both observation and theory. Remaining uncertainty persists in identifying a specific parent body. While certain asteroid families share characteristics compatible with the impactor, no single object can be named with absolute confidence. Orbital chaos over tens of millions of years obscures precise backward tracing. Additionally, some isotopic measurements overlap among related subtypes, leaving room for refinement as analytical techniques improve. What makes the outer main belt explanation compelling is its consistency across disciplines. Geology, geochemistry, astronomy, and computational modeling intersect in a way that reduces reliance on any one dataset. The asteroid's likely birthplace emerges not from a single discovery, but from accumulated evidence gathered over decades. In that synthesis, the story of origin becomes clearer. A fragment from a primitive, carbon-rich population, shaped in the earliest solar nebula and set adrift through resonance and time, journeyed inward until its path met Earth's. Long before oceans gathered in Earth's basins, before continents stabilized and life began its first quiet experiments, fragments of primordial matter were already cooling in the dark between planets. Primitive asteroids preserve this antiquity. Formed more than 4.6 billion years ago, they condensed from the same rotating disk of gas and dust that gave birth to the sun and planets. In their interiors, time has moved differently, with little melting or differentiation to erase their earliest structure. These bodies contain material that predates Earth's oceans by tens of millions of years. While Earth's surface has been continuously reshaped by plate tectonics, weathering, and biological activity, many carbonaceous asteroids have remained largely unchanged since the solar system's infancy. Their minerals locked in microscopic inclusions record conditions present in the protoplanetary nebula, where temperatures fluctuated and volatile compounds condensed into solid grains. Within these rocks are chondrites, tiny spherical droplets that once floated molten in the early nebula before cooling rapidly. Embedded beside them are calcium-aluminum-rich inclusions, among the first solids to crystallize around the young sun. Their isotopic compositions provide a chronometer for the earliest moments of planetary formation. By measuring the decay products of short-lived radionuclides, scientists reconstruct the timeline of accretion and differentiation that shaped the terrestrial planets. Organic molecules found in primitive meteorites add another dimension. Amino acids and complex carbon compounds detected in carbonaceous samples suggest that prebiotic chemistry was already active before Earth became habitable. The delivery of such material during early bombardment may have contributed ingredients necessary for life. In this sense, asteroids are not merely relics, but participants in Earth's own chemical history. Studying these bodies reveals planetary history because they represent building blocks that escaped the heating and geological recycling experienced by larger planets. Their densities, mineral phases, and volatile content help constrain models of how and where different regions of the solar nebula evolved. Comparisons between asteroid compositions and Earth's mantle inform hypotheses about accretion processes and the mixing of material across orbital distances. Recent space missions have brought fragments of these ancient worlds directly into laboratories. Sample return missions to near-Earth asteroids retrieved pristine grains protected from terrestrial contamination. Analyses of these samples under cleanroom conditions have confirmed predictions derived from remote spectroscopy while uncovering new complexities in mineralogy and isotopic ratios. Tiny particles returned from asteroid Bennu and Ryugu demonstrate the presence of hydrated minerals, indicating interactions with water early in their history. Such missions bridge the gap between distant observation and hands-on examination. They allow scientists to apply advanced techniques that cannot be performed on meteorites altered by atmospheric entry. Through high-resolution microscopy and mass spectrometry, researchers examine textures and isotopic signatures at scales unimaginable decades ago. A rock older than Earth's oceans carries within it the memory of a time when planets were assembling and the architecture of the solar system was still settling. By tracing these preserved fragments back through their chemical and isotopic clues, we gain insight into processes that predate the formation of stable seas and breathable air. The asteroid that ended the Cretaceous originated from this deep reservoir of primordial material, a relic from an era when Earth itself was only beginning to take shape. Where violence once reshaped the crust, there is now stillness. The Chicxulub crater lies mostly hidden beneath the northern edge of the Yucatán Peninsula and the shallow waters of the Gulf, its circular outline detectable not by sight from the ground, but by subtle variations in gravity and rock structure. From above, no towering rim announces its presence. Sediment has softened the scars, and time has folded the evidence into layers of limestone and reef. Across the peninsula, dense jungle spreads over what was once a zone of unimaginable energy release. Tropical forests rise from thin soils formed atop fractured bedrock. Roots thread downward into cracks produced by shock waves that traveled through Earth's crust 66 million years ago. In some areas, natural sinkholes called cenotes dot the landscape, their distribution tracing the ancient ring structure of the buried crater. Freshwater pools fill these openings, sustaining ecosystems that hum quietly under filtered sunlight. Life thrives in the very region where devastation began. Mangroves line coastal margins. Birds cross humid air at dawn. Insects move through undergrowth that conceals the geological boundary below. Coral reefs build slowly along nearby shores, their calcium carbonate skeletons layering over rock once vaporized by impact heat. The biosphere has not only recovered, but diversified, weaving complexity across ground that once glowed incandescent. The long arc, from destruction to human existence, bends through this landscape. In the millions of years following the impact, mammals expanded into ecological roles left vacant. Primates evolved within forests shaped by post-impact climates. Eventually, hominins walked upright, developed language, and cultivated memory. On the same planet altered by a celestial collision, human societies emerged, studied fossils, drilled into buried rock, and reconstructed the sequence of events that changed evolutionary history. Standing within the modern jungle, one moves across ground connected to that remote instant without perceiving it directly. The forest canopy does not reveal the geometry of the crater, yet its arc lies beneath. The limestone holds fragments of ejecta locked in mineral grains. Groundwater circulates through porous rock fractured by ancient force. Present tranquility rests upon foundations laid in a day of fire. This quiet aftermath illustrates continuity rather than contradiction. Earth absorbed the shock, climates stabilized, oceans cleared, and photosynthesis resumed. Over geological time, biodiversity rebounded and flourished. The extinction event, catastrophic in the short term, became a turning point that allowed new evolutionary experiments. The living world that surrounds us today exists partly because of that disturbance. Every moment of life unfolds within a system shaped by influences that extend beyond the atmosphere. Planetary surfaces record encounters with wandering bodies. Orbital mechanics determines long-term stability. Stellar evolution sets boundaries for habitability. The Chicxulub impact was one expression of these larger dynamics. Its consequences echo through the rise of mammals, the formation of ecosystems, and the emergence of beings capable of reflection. Now, the crater rests beneath forest and sea, its presence known through measurement and careful study. Birds call across canopy gaps. Fresh water gathers in circular pools. Human communities live and work above rock, once liquefied by heat. The aftermath is not silence, but renewal, a reminder that destruction and creation intertwine within Earth's deep history. From cosmic origin to quiet jungle, the path is long, and within it,